Hello everyone, I am Prasanna Kumar from CSM Section C. Today I will present my tech talk on the topic building a better hash function, which is part of data structures. Hash functions are important in computer science because they help store and retrieve data efficiently in structures such as hash tables, hash maps, and sets. In this presentation, I will explain how hash functions work, their properties, collision handling techniques, and their applications in modern computing systems. Introduction to hash functions. A hash function is a function that converts data of any size into a fixed size value called a hash value. This hash value is usually used as an index in the hash table, which allows a very fast data retrieval. One of the main advantages of hash tables is that they provide average time complexity of O of 1 for each search, insertion, and deletion. A good hash function should always produce the same output for the same input, which means it must be deterministic. Another important factor is minimizing collisions which occur when two different inputs produce the same hash value. Hash functions are widely used in data structures, cryptography, and distributed systems. Hashing. Mathematical foundation of hashing. Mathematically, a hash function maps a key from a large set of possible values to a smaller range of indices in a hash table. This can be written as h of k gives rise to 0, m minus 1, where m is size of the table of the hash. Ideally, the hash function should distribute keys uniformly across the table. If keys are evenly distributed, the probability of collisions become very small. Another important concept is that load factor represented as alpha is equal to n by m. Here, n is the number of elements stored and m is the size of the table. When the load factor increases, collisions become more frequent and performance decreases. Properties of an ideal hash function. An ideal hash function has several important properties. First is uniformity, meaning hash values should be evenly distributed across all buckets. Second, Second is determinism, meaning the same input always produces the same hash output. Third is efficiency, meaning the hash function should compute quickly. Another important property is that avalanche effect, where a small change in input produces a completely different hash value. Finally, the function should have a low collision rate, ensuring efficient performance of the hash table. Common hash function designs. There are several methods used to design hash functions. One the common method is the division function, where the key is divided by the table size and the remaining is used as the hash value. Another important method is the function multiplication method, which multiplies the key by a constant part and extracts the fractional part. Universal hashing uses a family of hash functions and randomly selects one to reduce collision probability. For strings, a polynomial rolling hash is often used. Another approach involves bit manipulation techniques, which combine shifts and XOR operations to produce better distribution of hash values. Collision resolution strategies. Collisions occur when two different keys map to the same index. There are several strategies to handle collisions. One method is to separate chaining, where each bucket stores a linked list of elements. Another approach is open addressing, where all elements are stored directly inside the hash table. In open addressing, probing methods are used to find the next available slot. Examples include linear probing, quadratic probing, and hashing. Choosing the right collision resolution strategy helps maintain efficient performance. Analyzing hash function performance. The performance of a hash function is measured by how efficiently it distributes keys. How for separate chaining, the average search time is approximately O of 1 plus alpha, where alpha is the load factor. As the load factor increases, the number of collisions also increases. Cache performance also plays an important role. Methods like linear probing perform well in terms of memory locality because data is stored in contiguous locations. Statistical tests such as chi-square are uh, used to measure the uniformity of hash distributions. Designing a custom hash function. When designing a custom hash function, several factors must be considered. First, we must analyze the input data structure such as whether keys are integers, strings, or objects. Next, we choose the table size, which can be prime number or a prime power of 2. The hash function should avoid patterns that may cause clustering. There is also a trade-off between speed and quality. Faster hash functions may produce more collisions, while stronger functions may require more computation. Proper testing ensures the hash function performs well across different datasets. Case study: string hashing. Strings are very common keys in many applications because strings have variable length. Designing efficient hash functions for them is important. One popular example is the DJB2 hash function, which uses bit shifting and addition. Another example is Java string.hash code, which uses multiplication with a constant value such as 31. Another widely used algorithm is the FNV hash, which combines XOR operations and multiplication. These techniques help distribute string values more evenly across hash table buckets. Tabulation. Tabulation hashing is an advanced technique used to improve hash distribution. In this method, the input key is divided into smaller parts, usually bytes. Each part is used as index in a pre-computed random table. The values from these tables are the combined using XOR operations. This technique provides strong randomness and reduces clustering. Tabulation hashing is simple to implement and performs well in many real-world systems. Murmur hash. Murmur hash is a fast non-cryptographic hash function designed for high performance. It uses a combination of bit shifts, multiplication, and XOR operations to mix the input data. Murmur hash produces a strong avalanche effect, meaning small changes in input create large differences in output. It is widely used in systems such as databases and distributed storage platforms. Compared to older algorithms, Murmur hash provides better speed and fewer collisions. Hash function security and adversarial inputs. In some systems, attackers may exploit predictable hash functions. For example, a malicious user might intentionally create many inputs that produce the same hash value. This can cause performance to degrade from O of 1 to O of n, resulting in denial of service attacks. To prevent this, secure hash functions such as SIP hash are used. SIP hash uses random keys and multiple mixing operations to prevent attackers from predicting hash values. Security considerations are important when hash tables process user generated data. Optimizing for modern hardware. Modern computer hardware can influence the performance of hash functions. For example, SIMD instructions also allow multiple operations to be processed simultaneously. Cache-friendly algorithms improve memory access speed. Branchless programming avoids conditional instructions that slow down pipelines. For hardware instructions such as CRC operations can accelerate hashing. Proper data alignment, and memory layout also improve performance in large-scale systems. Evaluating hash function quality. To evaluate hash function, several metrics are used. The first is collision rate, which measures how often collisions occur. Another test is the CHI square test, which compares expected and observed distributions. The avalanche test measures how many output byte change output bits change when one input bit is changes. Performance benchmarks measure execution speed. These evaluation methods help determine whether a hash function is suitable for real applications. Applications in AI and machine learning. Hash functions also play an important role in AI and machine learning systems. One example is feature hashing, also known as the hashing trick. This technique reduces high dimensional data in a smaller representation. Another application is locality sensitive hashing, which helps find similar data points quickly. In distributed machine learning systems, consistent hashing is used to distribute data across multiple servers. These techniques enable scalable machine learning on large datasets. Emerging trends and research dimensions. Emerging trends and research directions. New research is exploring learned hash functions where machine learning models help generate better hash mappings. Neural networks can also produce compact binary codes for similarity search. Modern systems are exploring hardware acceleration using GPUs and TPUs. Researchers are studying hashing methods suitable for new memory technologies. These innovations are helping improve performance in large scale computing systems. Best practices and guidelines. When choosing a hash function, engineers should consider the specific application. For example, murmur hash is good for speed while zip hash is useful for security. Hash functions should always be tested on real characters. Choosing the correct table size and collision resolution method also improves performance. Proper documentation is important when designing systems that rely on hashing. Thank you for listening to my presentation. I hope this presentation helped you understand the importance of hash functions and how they are designed for efficient data structures. Thank you.